Okay, Anna, are you watching? I think you're the email I got. If you're able to hear me, can you just go ahead and type something in the chat box there? I want to make sure my audio is working. Okay, I'm just going to give it another minute or two to see if anyone joins in before I jump into tonight's lecture. I'm hoping the one viewer that is there is able to hear me. If not, let me know. Type something in the chat box so I know what's going on. This is Geology 1550 Intro to Earth Science. This course is going to be covering some basics of geology, meteorology, a little bit of astronomy. This is the first time we've done it online, so any feedback that you as students can give would be extremely helpful. I'm going to go ahead and get started here. Okay, to start out, each week you're just going to click on the folder on the left-hand side of your Blackboard. So this week is week 1. You click on that folder, go into the contents. Like I said, every Monday at this time, I am going to be doing a live stream of the lecture where I'll go through the slides with you. The only time that would change are in weeks 7 and weeks 11 where you have an exam. And I will announce that ahead of time, but because of the exams, our weekly schedule is going to get shifted a bit. So this week you have the live lecture. It's going to be a really short, just general overview, introduction to the course and textbook. You're going to have a simple homework assignment just to get you using the scientific method. That's something that we really emphasize in this field. The process of developing an idea and testing it and presenting your findings. It's a very defined, strict process. We don't just, as scientists, make something up off the top of our heads and decide it's good. So there's an actual method to follow. So that's your homework assignment this week. And then in your Mastering Geology program, you should have all gotten an access code with your textbook. If you didn't, you can go to Pearson Publishing, go to your textbook, and you can purchase an access code. The majority of your homework is going to be done through Mastering Geology. So you're going to need that access code to do your homework assignments. There's also a lot of additional study guides, virtual field trips on there that really accentuate a lot of the topics we cover in this class, things that I'm not really able to present to you as much as I would like. So make sure you have that. You have to have that for your assignments. What's that? So you have a scientific method assignment for me. You should have one very brief learning how to use Mastering Geology assignment, and that is it for this week. If you want to start looking ahead, you can, but you're not required to. What else? You can contact me by email. I check my email every day, at least once a day. On the left-hand side of Blackboard, you have a question board. That is where you can ask any earth science-related question. It doesn't have to be related to the class. I mean, it has to be related to earth science, but it doesn't have to be, very lesson-specific. If you have a question about, I don't know, what size black hole would need to develop to, destroy the Earth, go ahead and ask that. And, if I can't answer it, maybe one of your classmates can, or if your classmate asks a question and you think you can answer it, please jump right in. I really want you guys to be helping each other out with these topics. So, you will have 2 exams. Yes. Oh, sorry, 3 exams. And if you heard that, that's the cat. He's a little whiny tonight. And if anyone needs any extra questions answered before the exams, like I said, you're more than welcome to ask on that question board or email me. So why don't we go ahead and we will get started. So like I said, this is Earth Science Geology 1550. So what is Earth Science exactly? So Earth Science is essentially the study of the Earth and the processes that formed and change it. So it's how the Earth formed, how the Earth is forming, how it's changing, and what controls, all the processes that occur on Earth. It is a multidisciplinary science that includes geology, oceanography, meteorology, and astronomy. Now, my personal background is geology. I have a bachelor's degree from Miami University in geology. I am working on a master's in environmental pollution control. I have some background in oceanography. I do my best with meteorology and astronomy, but those are my less strong points. So I'll be the first one to admit that if you ask me a question on that one, there's a good chance I will say I am not sure. Let me go look that up and get back to you. Okay, but I will do my best. Earth is a dynamic planetary body with many interrelated parts and a complex history. So the Earth is always changing. It is not static. Climate change, obviously, but even with, continental placements in the oceans, those are still moving and changing in a dynamic system. It may seem like it's stationary and it doesn't change, but it's a very slow process, and they are always shifting in relation to each other. Sorry, my cat's on my lap now. Many political, economic, and moral issues exist within the framework of Earth science. For instance, funding for renewable and non-renewable energy sources. I guess in New York, that fracking is not allowed. However, down, just a few minutes away in Pennsylvania, fracking is. But an understanding of, the geology underlying structure is important for getting funding to explore these gas deposits, or trying to convince states to let you drill there, and an understanding of the impacts you have on the earth and the subsurface, and for getting permission to drill in certain states. Funding for planetary exploration to learn more about how the earth works. Developing mineral deposits in the U.S. and other countries, so like I said, with the fracking or with the natural gas. Using pesticides and herbicides to improve agriculture, sorry. Coastal city development, understanding how the coasts of continents are constantly changing, and mitigation of coastal changes or acceleration of coastal changes, human impact. We may think that we are mitigating a problem, but we may just be exacerbating another one. So we have to understand the dynamic nature of these coastlines to understand how the city development along them impacts them. Carbon taxes to abate CO2 emissions. This is a very hot topic nowadays about the carbon tax and carbon caps on a lot of power plants and production plants and factories, and the trade of a carbon tax. Water usage in the U.S. and many other countries, and future water wars. Water is a scarce resource, and when we're talking about fresh water, there are areas where it is very hard to come across fresh water, and it's becoming a bigger issue as waters are becoming polluted, or as aquifers are becoming overpumped and drained at an accelerated level. Let's move on. Okay, so the four spheres of the Earth. In the broadest sense, there are four spheres that interact with each other on the Earth. The hydrosphere, which is the water portion of the planet. And when we talk about that, we're talking about oceans, groundwater, and rain and clouds, the entire water cycle. The atmosphere, which is the gaseous portion of the planet, the Earth's thin envelope of atmosphere of air. And so, the air from the surface up to, a few tens of kilometers, hundreds of kilometers above the Earth's surface. We will be getting into that towards the end of our semester together. The geosphere, so the solid and liquid Earth beneath the hydrosphere and atmosphere. This is the largest sphere in volume. Essentially, this is what makes up the actual body of the Earth. We're going to be focusing on this for the first few chapters within the semester, really understanding what makes up the geosphere and how it's changing and how it impacts the other spheres within the Earth. And finally, the biosphere. This is the totality of life on Earth and the parts of the hydrosphere, atmosphere, and geosphere where living organisms can be found. Now, this one is also a very important sphere and understanding, dynamic landscapes, but we will not be touching on this one quite as much as the others. When we talk about earth science, we're talking more about the non-organism portion of Earth's processes. So we won't really be touching on the biosphere except sort of a tangential to whatever other topic we're covering at the time. So the hydrosphere, this just breaks it down a little bit for you to kind of understand where water is found on Earth. So if you look on the left-hand side, we have a column of water representing all the water on Earth. Okay, fresh water makes up only 2.5% of all water on Earth. Saline water, such as oceans and saline groundwater, and salt lakes like the Great Salt Lake, that makes up almost 97.5% of all the water on Earth. So the vast majority of water on Earth is saline water and is unsuitable for human consumption. Saline groundwater in lakes makes up almost 1% of Earth's total water. So when we talk about fresh water, like I said, it's about 2.5%. Now, out of that 2.5%, groundwater contains 0.77% of the totality of Earth's water. And glaciers they contain 1.76% of the total Earth's fresh waters, or total Earth's waters. Okay, so the difference between the groundwater and glaciers, what's left over, that's what's in our streams, our lakes, trapped within the soils. the water that's easily accessible for consumption. Sorry, I have to get off now. Okay, so streams and lakes, they account for 0.03% of the fresh water on Earth. 69% of it is trapped up in glaciers. So the vast majority of the fresh water on Earth is currently trapped within glacier systems on Earth's surface. And finally, groundwater represents less than half, like we said, less than 0.5% of all the water on Earth. However, it accounts for 30% of all fresh water on Earth. So, or less than 1% of all waters on Earth, and that is 30% of our total available fresh water. Okay, and then the groundwater is 96% of all liquid fresh water. So if we take glaciers out of the equation, the vast majority of fresh water available on Earth is within groundwater aquifer systems. Okay, so the global ocean, so salt water, covers 71% of Earth's surface and makes up 96% of Earth's water. So this is by far the largest natural resource and the largest component when we talk about the hydrosphere. Most of the liquid is trapped within this system. Okay, when we talk about the atmosphere covers from Earth's surface, so 0 kilometers in altitude, to about 120 kilometers in altitude. When we discuss this in later chapters, we're not going to get too far up into the atmosphere. We're going to stay in the lower levels, so about 80 to 100 kilometers is what we'll talk about. But if you look at the chart on the bottom right, you can see that average sea level pressure is slightly more than 1,000 millibars. Okay, so when we talk about air pressure, we're relating it to the sea level air pressure. And if you look at the graph, 50% of Earth's entire atmosphere is below about 5.8 kilometers. Okay, so from 5.8 kilometers in altitude down, that is where 50% of our entire atmosphere is. Okay, when we get up to the top of Mount Everest at about 8.5, okay, the air pressure there is 314 millibars, which is 1/3 of that of sea level. So you can see we're getting to the point where probably 2/3, probably 67 to 75% of Earth's atmosphere is below the elevation of Mount Everest. By the time we get to 16 kilometers in altitude, 90% of Earth's atmosphere resides underneath that curve. So the further up you get in the atmosphere, the less actual air that there is. So most of what we're going to focus on is about 16 kilometers down. Okay, quickly on the biosphere. This is just a brief breakdown of general numbers of species on Earth. So there are about 7.8 million animals that are known on Earth. 298,000 plants, 611,000 known fungi or molds, 36,000 protozoa, 28,000 algae, and more bacteria than we are capable of counting at this point. And so the biosphere is extremely large, encompasses a wide variety of organisms in different environments, and the ocean contains a significant portion of this biosphere. And modern coral reefs contain about 25% of all marine species. Because of this, they're sometimes referred to as the ocean equivalent of rainforest. And rainforests are some of the most varied environments on Earth. They are typically characterized by hundreds of different species per square kilometer. They have the largest biodiversity on the planet, and that's why the concerns about the loss of these rainforests and coral reefs is extremely troubling, because as we lose these, we lose the biodiversity, and we lose some organisms that are extremely important to sustaining life on this planet. The geosphere. This is my favorite sphere. So I'm sorry for talking a little bit about this. So when we talk about the geosphere, first we're going to look at just a very basic breakdown of the planet Earth. So on the right-hand side, we have a breakdown of the layering by chemical composition. So this just shows how the interior of the Earth is divided based on differences in composition. So we have the crust, which is low-density rock, and it ranges from 7 to 70 kilometers thick. Okay, so the crust is what we examine and study. You know, when we drill, we're drilling through the crust. You know, any sort of drilling activities have never penetrated to the mantle, which is the next layer. This is high density rock. Okay, this is solid material. And then when we get down about 2,890 kilometers into the center of the Earth, we reach the core, which is composed of iron and nickel. Okay, so these are just a breakdown of the different compositions of the Earth's interior. On the left-hand side, though, we look at physical property breakdowns. Okay, so first we have, sorry guys. First we have a breakdown of the lithosphere, or the crust. So on the crust we have continental crust and oceanic crust. And these actually have two different chemical compositions and different physical properties, which we will get into, I think, in chapter 3. Okay, so that's what we really are familiar with and study, is that thin crust unit. So below that we get into the lithosphere. This is solid, it's about 100 kilometers thick. Okay, the lithosphere resides on top of the upper mantle. The upper mantle is also called the asthenosphere. It is solid but mobile. Okay, so it can be, it's very plastic. It can be shaped and molded. It reacts to movement and impact from the lithosphere. And then once we get down from the upper mantle, about 600 kilometers down, we get into the lower mantle, which is solid. So the upper mantle is solid, but it's still a bit plastic and mobile. It can be manipulated a bit. However, the lower mantle, from our understanding, is solid. Again, about 2,800 kilometers, we reach the outer core. And like we said, the core is iron and nickel. However, the outer core is liquid. And it's scientists' current belief that about 5,000 kilometers into the Earth's interior, we reach the inner core, which is also a composition of iron and nickel. However, this is solid material. So we have just kind of a focus question I want you guys to think about here. How and why is oceanic crust different from continental crust? I briefly stated that there is a difference there. So that's one thing I want you to kind of think about moving forward. We're not going to really get into that right now. But that will come up in later chapters. So I really want you to kind of keep that in mind. So like I said, the Earth and its system surroundings are a dynamic system. Okay? Our past impacts our present, and our present impacts our future. They're constantly interacting, and these parts, they may be independent or interdependent, but they form a whole. You may have heard me use the term dynamic system a bit. So dynamic means it's constantly in a state of change or flux. So even if we can't see it, a lot of the Earth's environment are actually dynamic. So the Himalayas, they're mountains, they're big, they're old, they don't change. They are actually a dynamic system, constantly in a state of change. They are constantly in a rate of deformation and of erosion and of spreading. So it really kind of changes our concept of what is stationary and what isn't when we look on a much broader scale. Speaking of scales, so the Earth contains vast scales. Natural processes in the Earth system act on spatial and time scales on a large range. Spatial scales of nanometers to billions of kilometers. Looking at the solar system, the galaxy, and the universe, that's distances that the human brain can't even comprehend. And we're talking about time. We're looking at milliseconds, for a rainstorm to occur in seconds and minutes, to billions of years in time for geologic formations to be deposited and to lithify into actual rock. So we can look at things on a very small scale that occur in a very short period of time to things that take millions of years to occur. And it's important to note that the Earth is a closed system, except for energy. So the solar energy that comes in is the only sort of input that we get. So when we talk about a closed system, it means that all the systems within the Earth interact with each other, but there is no outside force acting on them, and the systems within the Earth are not acting on another force outside of the planet. It is self-contained. It can exist essentially on its own, with the exception of solar energy that provides life. Okay, now getting into what you're going to need to know for your homework, talk about how we study the Earth system. So we study it using science. Science! Do you guys watch Bill Nye ever? That's what this reminds me of. Anyway, so science is a way to discover underlying patterns in the natural world. So it allows us to make predictions regarding what should and shouldn't happen. And we use science to try and explain cause and effect of phenomena. So this is really what we use to try and understand the world around us and figure out what's going on. Science also assumes that processes in control are understandable, that it's something that if we study it long enough and examine it long enough that we will come to an understanding of what's happening. It also assumes that the same underlying physical processes today acted in the past and will act in the future. So, gravity has not changed. It's always a gravitational acceleration of 9.81 meters per second squared. And it will always be 9.81 meters per second squared unless something changes in the Earth's mass. And science also supports an explanation that best explains all observations. And when we say this, we mean that our current understanding is only based on the observations we're able to make. We may make observations in the future that would change our explanation because now we have a new best fit based on updated observations that could change an understanding. So, the scientific method. So, when you use the scientific method, you start out by making observations. Scientific method always starts with an observation. I see that it gets brighter in the morning and it gets darker at night. And so step 2 is ask questions. Why does it get brighter in the morning and why does it get darker at night? Okay. So step 3 would be to develop a hypothesis. Come up with a possible explanation of this. I could come up with an explanation that there's a giant with a flashlight who turns it on at 7 a.m. and turns it off at 9 p.m. But then I would have to go to step 4 and test this hypothesis, experimentation. Okay, I would have to figure out a way to test this or to conduct an experiment to determine if this is correct. At step 5, we would evaluate the hypothesis based on the test performed in step 4. So we would draw a conclusion about the hypothesis. Typical questions would be, was the hypothesis proven or supported? My giant hypothesis would probably not be proven or supported. So it would be disproven. And then given the results, what are the next steps that need to be taken to answer the questions of interest? So you may develop a hypothesis and test it and evaluate and come to the conclusion that you don't have enough information to support your hypothesis fully. It may be inconclusive, and then you would need to redesign your hypothesis to conduct more experiments to come up with new conclusions. Okay, so it's an ongoing process. What is a hypothesis, you ask? I'm sure you didn't, but you're going to learn. A hypothesis is a tentative, testable statement about the general nature of the phenomena observed. It is not a hunch and it is not a guess. Okay, it has to be testable. Okay, you have to be able to go out and conduct an experiment to determine if it is plausible or not. A theory is a well-tested and widely accepted view that explains observable facts. For example, the theory of evolution, the theory of relativity, and the theory of plate tectonics. Again, these are not hunches or guesses. These are hypotheses that have undergone multiple experimentation and testing and have come to reasonable conclusions based on the observations and based on those experiments, and this is our best explanation to date on these. Okay. And then a law is a concise statement that expresses a fundamental principle of science, which is confirmed and broadly agreed to. For example, the law of gravity. Okay, so this is a fundamental principle that is widely accepted, that has been supported by any testing, any experimentation, has not been refuted. In science, with the scientific method, it is highly unlikely that you will get someone who will say that something is fact and it is absolute, because there's always a chance that something will be discovered later on that will contradict it. So we talk about them as being principles that are confirmed. Okay, they're confirmed, but they're not absolute. There may be findings that could alter it down the road. Okay, so this is looking at your question or your homework question. This is images of the Emperor Seamounts and the Hawaiian Island chains. When you look at your homework assignment, you'll see that there are numbers on each island on both the Hawaiian and the Emperor Seamounts, and these refer to the island's age of formation in millions of years before present day. So when we look at the Nintoku Seamount right here, okay, this formed 56.2 million years ago. Okay, and then we look at the Midway, and that formed 27.2 million years ago. Okay, so this that's what these numbers represent. So 56 million years ago and 27 million years ago. Okay, so you're going to make some observations just based off of these images, and you're going to come up with what questions you would ask. So look at these, try and figure out what questions you would ask about these islands or seamounts and their ages, develop a hypothesis, and figure out how you would test the hypothesis of this. Oh, there we go. Science comes with its own strengths and weaknesses. So one strength of science is the objectivity. It's based on facts, and it should, in theory, be unbiased. Scientists are supposed to take a very unbiased, straightforward approach to what they're examining, and draw conclusions based on observable, measurable facts. Okay, personal opinion or influences should not come into play when making a scientific decision or writing a scientific paper. Reproducibility. So if you conduct a scientific experiment, you need to be able to demonstrate that the same result will occur anytime that test is run. Okay, this increases confidence that it's true. So if I conduct a test, I could give my step-by-step guide to a team in Europe, and they could take that and they could reproduce my test exactly and get the same results. So science is progression or efficient and goal-driven. And one result is the starting point for a new sequence of question and tests. So every time we reach a fact or a finding, this is usually a launching point for a deeper investigation. And it has a predictive value. Okay, results help establish ground rules. The results of early scientific endeavors have given us the law of gravity, theory of plate tectonics, really helping us get a basis for concepts as we move forward. However, there are limitations. So it is restricted to physical evidence. We're basing all of our science off of measurements made by our senses or our technology, and our technology is limited by our current understanding. So it is possible that we don't have a full, complete understanding of the world around us because our technology is not capable of it. Cannot use hearsay, opinion, or tradition, and can be influenced by human bias. So like I said, scientists are to only go with facts, observable, measurable, but humans are fallible, and it is almost impossible to completely keep personal bias out of science. Limitation of science also assumes that the rules don't change. So science is not capable of dealing with miracles or divine intervention. There is just no way for the realm of science to really kind of accept divine intervention and scientific fact. It's very difficult in the field of specific scientific endeavors. And accepts as valid only results that are repeatable. If you get a result and no one else can repeat it, it is not going to be accepted as a valid scientific finding. Another limitation is it proves nothing. All conclusions are provisional. So like I touched on earlier, science attempts to disprove and reject hypotheses and accepts hypotheses that cannot be disproved. Okay? So if a hypothesis is currently incapable of being disproved, we accept it as proven, with the understanding that there's always a chance for it to be disproven down the road. Okay, I'm not going to play this for you. I want you all to kind of just watch this on your own. If you can't get the video to play, click on the link down here and just copy and paste it into your browser. This is a 10-minute video on why Mars died and Earth lived. This is the basis for your discussion questions for this week, so I want you to really take a few minutes and watch this and answer your discussion questions. Go see what your fellow classmates have had to say about this video. And finally, cute little pun, okay? So this is a little comic strip from the NIH grant. It says, "You are completely free to carry out whatever research you want, so long as you come to these conclusions." It's kind of a backhanded way of making comments on how government agencies may go about giving out grants. Human bias comes into play there. So, well, my one person who tuned in live, I hope this went okay and it streamed okay. If not, please let me know. Like I said, this will be posted on YouTube at the link for everyone to come back and view at a later date. The next lecture will be Monday at 8 o'clock in the evening. That one's going to be a little bit longer. We're going to get into some real material. And in the meantime, if anyone has questions on any of the topics covered here or your homework, feel free to email me. I think you have my phone number in there too, so if you want to text me, if you have to have it answered right away,